Okay, so today we're going to be dealing with the conservation of energy question. So in this question we have a roller coaster that starts from here and ends up at this point here. Now at the top of the hill here, the roller coaster's velocity is 0 meters per second, and it's at a height of 70 meters. Here at the loop-de-loop, it has a height of 40 meters, and for part A, we're looking for the velocity at that point. Now for part B, we were given the velocity here to be 30 meters per second, and we are supposed to be finding the mass. Sorry, the height. And for this, we're going to be using conservation of energy, and so what that states is that the total energy of a system is equal to the kinetic energy of that system plus the potential energy of that system. Now, from our formula sheet, we can say that this is equal to 1/2 mv squared plus mgh, and we know that this is true for any point in the system. Any system will have total energy equal to the sum of the other energies that comprise, and in this case, and in Physics 20 in general, those are going to be for you kinetic energy and potential energy. Now, we can take into consideration here that we have a total total energy, and simplifying this, we can say that for the top point for this entire system, actually, at any given point, we can calculate the total energy, and that total energy is going to be equal to the energy at this top point. We use this top point because we have all the information necessary to solve for that point. So what we're going to do is we're going to calculate that real quick. So E total equals 1/2 m v squared plus (9.81) times 70 meters times mass. So, rounding the acceleration of gravity to 10 meters per second squared, what we're going to end up with, since this goes to 0, is that ET equals 700 m. M being not meters, but rather the units m for mass. So this here is mass, not meters. Okay? And so now to solve this question for the velocity at point A, we'll use the same technique now given that we know m. So we can go ahead and do that. We can say that at point A here, we'll call this point A, at point A, ET equals EK plus E potential, which is equal to, so 700 m equals 1/2 mv squared plus mgh. Now, the masses here are all the same, since the mass of the roller coaster doesn't change. So then we can cancel these out, and now we're left with 700 equals 1/2. We're looking for V, so we can call this VA squared plus g, which will round up to 10, and the height, which is 40 meters. Now, simplifying this, we're going to end up getting 700 minus 400 all times 2 equals VA squared. And we're gonna get that VA squared equals 700 minus 400, which is 300, times 2, which is 600. And the square root of that is 24. So VA equals 24 meters per second, approximately. So we'll make these approximately 24 meters per second. Now for part B, we're asked to find the height, and we're given the velocity. Now for this, we're going to do the exact same thing as for part A, so we'll call this up here part A. And we'll go ahead and write here part B. Now in part B, we're going to do the exact same thing, because like I said earlier, the total energy of a system is the same at every point in that system. So we're going to have, again, 700 m equals 1/2 mv squared plus mgh, and again the masses will cancel. Now here we're given the velocity, so we can go ahead and plug that in. 700 equals 1/2 times 30 squared plus 10 times the height. And so we're going to get that, we're going to get 30 squared, which is equal to, let's just plug this into my calculator, I believe it's 900. But better to be safe than sorry. It is in fact 900, so 700 equals 900 1/2 plus 10h. So 700 minus 450 plus 10, oh sorry, yeah, 700 minus 450 equals 10h. Now we're going to get from this that $250 equals 10h, and as such, h is going to equal 25 meters. So we saw that we didn't have to use any circular motion even though we were dealing with the circle, because of the fact that energy in the system is equal at all points. I hope this was a useful tutorial, and I'll be posting more soon for you guys to look at.